Okay, welcome everybody. Welcome back to Regis. We are in our 7th week, which means the Regis program is almost done, the summer program at least. So thank you so much for sticking with us. I'm quite excited about this talk. But before I introduce this next talk and the next speaker, let me say that because some of you know, we might be being hit by a tropical storm slash hurricane tomorrow. Some of our activities may not happen tomorrow. So in particular, by now, we will have to cancel Python for physics, which should have been taking place tomorrow at 1 p.m. So we're going to cancel that. But don't worry, everything that was going to be covered, we'll cover up later. The later talk is still scheduled to take place. Okay, so just keep track of the schedule as we update it. Okay, so focusing now on today's talk, it's a real pleasure to introduce Carlota, Dr. Carlota Andres, who is she's currently a postdoctoral fellow in the Theory Center at Jefferson Lab, which is where I work as well. But she actually is about to leave us, and this is her last week with us. And just to give you a little bit of idea of what maybe let me start with a little bit of background. So her background, she got her PhD, her undergraduate degree and PhD in the University of Santiago de Compostela in Spain. And she's an expert in theoretical nuclear physics. In particular, her interest is on nuclear structure, heavy ion physics. If these words don't make any sense to you, don't worry. She's going to start introducing these things. And now let me mention that the reason where she's leaving us because she's now been offered 2 jobs, which is uncommon in the field. So she's going now back to Europe because she got another fellowship, another research fellowship in Portugal. But in addition to that, she got a Marie Curie research fellowship. If you don't know who Marie Curie is one of the most important scientists of the last century. She got 2 Nobel Prizes, which is rare, and getting a fellowship after her name. These are highly sought after fellowships, and so it's a real privilege to obtain one of them. So on that note, it's a real privilege to have Carlota join us before she goes on and proceeds in her wonderful career. So she's going to be telling us about how do we look at the proton at Jefferson Lab. So with that, take it away, Carlota. Thank you so much.
So thank you, Raul. Thank you very much for inviting me to participate in this amazing summer program. I'm very happy actually to be here. This is not only my last week as a postdoc at Jefferson Lab, but also my last talk as a Jefferson Lab postdoc. And I think it's cool that it is something like this, something with a different audience that I think it's very important to get engaged with. So today we are going to talk about one of my research lines, which is the structure of hadrons and particularly the proton. So don't worry if at the beginning there are some words that sound like a little bit complicated because I go from the beginning. And the title of my talk is Looking Inside the Proton at JLab. And I say looking here because that's what we are going to do, basically. That's what we do at JLab. JLab is like a giant microscope that basically allows us to look inside the proton. But to start by something that you all know or you are all familiar with, we're going to start with a little bit of history of what a proton is, and before what a proton is, what an atom is. So I think most of you have heard about atoms, and probably most of you have heard about the Dalton theory. So Dalton was the first scientist to talk about atoms, and he basically proposed that chemical elements are formed by some particle that he called atoms, and he thought they were indivisible. Now we know that that's not totally right. We can divide atoms into his components, so they are not indivisible. But this was a great breakthrough in the 19th century because he was the first person to say, hey, if something is hydrogen, hydrogen is formed by a given atom, and if something is oxygen, this is formed by another atom, and these atoms are always different, but all the atoms on the oxygen, according to him, were equal. So that's something that we nowadays all study, like the periodic table of elements and things like that. So this was the base for this kind of things that we study in chemistry. He also said that, for instance, if you have water, which is H2, H2O, you basically have always this proportional, twice hydrogen than oxygen. So he did many things that were correct, apart that he said that they were indivisible. And this was a great breakthrough. And this comes with the idea that we have to start questioning things. So whenever someone tells you something, some statement about science, the important thing is not to memorize what they say, but to question if that makes sense and if this can be possible. So in the late 19th century, Thomson discovers the atom. So he breaks a little bit this theory of Dalton that the atoms are indivisible, because he finds a particle that is inside the atom and that they call electron. And he did it with this experiment that we see here. And the experiment is pretty simple right now, but it was very important at that time. And basically, he put a voltage here between these two metals that we call the cathode and the anode. And this creates a current. And this current has a charge. So what happens with a current when it has a charge is that if you put a magnet here, instead of going in a straight line as it was going, before the magnet, the trajectory gets deflected. And he realized that it was all in this deflection that happens here. It is related to the mass and the charge of the particles constituting the current. So he realized that when he was changing the cathode by different elements, different metals, we put lithium or sodium or any other metals, this trajectory was always deflecting in the same way. So for him, it was obvious that this current has to be formed by a given particle, that it was present in all these elements, no matter if it was lithium or sodium, it was always the same particle with the same mass. And this particle was named electron. It also happened that that this deflection couldn't be that the mass of the electron was to be tiny, much tinier than the mass of the atom. So according to him, the electrons had to be much smaller than the atom, and they were a part of the atom. So this was like the picture of Thomson of the atom, and as he didn't know about the proton that we know nowadays, for him it was something that was positively charged, like a soup of positive charge, and then the electrons. So this is not totally correct, we know nowadays, but it was a great and important thing to discover the electron. Then on the 20th century, we have Rutherford, and Rutherford did another experiment that basically consists of having here alpha particles. So basically he had here a radiative element that naturally emits this alpha particle. Alpha particles are what we know now that they are nucleus of helium. So basically they are positively charged particles. And he created this beam of positive particle and make it scatter with a fine, thin layer of gold. And what happened is that if you believe that Thomson was right, so that we had like this soup of positive particles with some electrons there, the alpha particle should go in a straight line, shouldn't change their trajectory because the electric field created here would be not strong enough to deviate the trajectory of the particles. So all the particles should go in a straight line like here. But what he found is that most of the particles were going in a straight line, but some of them were deviating. And more particularly, a few of them, very few of them, were deviating a lot, which is these ones that go here, that go backwards, like more than 90 degrees, which corresponds to this trajectory here. And this made him think and realize that basically the positive charge couldn't be all around the atom, but has to be located in the center. And only the particles who were like going through the center of the atom will be the ones deflected in large angles. And with this, he had this picture of the atom that is more similar to what we know nowadays, where you have the protons in the center and then the electrons around. So he realized that the atom was mostly empty, which is something that we know nowadays that it's correct, and the proton was in the center. But still there were things missing, because I know that most of you have heard about the neutron, for instance, and the neutron was discovered later because the neutron has no charge. So as there is no charge, it's more difficult to run experiments about the neutron. And this was discovered in the 20s. And the first thing they discovered is that you have atoms of the same element that were not exactly the same. that they have a slightly different masses. And now we know that this is due to the fact that they have the same number of protons and electrons, but there can be atoms of the same element that have a different number of neutrons. So Chadwick discovered the neutron, and he had this picture of the atom, which is more similar to what we have right now. Still is not completely correct, because now we know things like quantum mechanics that makes a little bit more complicated this picture, but it's more or less accurate with the protons and the neutrons on the center, which is actually very, very small. Like you have a nucleus. If you want to imagine an atom, you can imagine a stadium. I'm thinking of putting a ping pong ball in the center of the stadium. So that would be the nucleus, and the rest of the stadium will be like completely empty, except for a few people sitting around, like in the seats, and this would be the electrons. So you can imagine that the nucleus is much more smaller than the rest of the atom, and most of the atom is empty. So the question to us is if these protons and neutrons are fundamental particles. So fundamental particles, well, what physicists call fundamental particles is particles that are indivisible. So the electrons, for instance, are fundamental particles. They cannot be divided into other particles. They are not formed by other particles. So one interesting question to ask is, are protons and neutrons fundamental particles like the electrons, or they are different? And the answer came in the 60s with different experiments in the SLAC, where they discovered that both protons and neutrons have internal structure. So I know this plot here is not like the easiest thing to understand, but what I want to show here is that they've performed some experiments, and in these experiments, they measure the number of particles going in different angles. So here you have the angles, and this would be similar to the number of particles. And these points that we see here with these error bars are the experimental data. So basically, they have theories. So they have theories saying that if the proton and neutron were fundamental particles, so what we say now point-like particles that cannot be debated, this data point should go in this line that we see here. But they were not going in this line, but in this line here. So that means already that the protons and neutrons should be formed by something else. But what is that something else? So these particles that are inside the protons and neutrons are called quarks, and they were discovered in SLAC. SLAC is an experiment that well, now it doesn't exist anymore, but ran for many years in Stanford University in California. And the idea of these experiments is to create like a giant microscope to see what is inside the proton. So the idea is that if you threw electrons to a proton, so this should be an electron, these electrons emit light, something that we call photons, but this is basically light. So if you manage to emit light with a wavelength, the wavelength is this lambda here, which is the difference of this between these two maximums here, with a wavelength that this is small enough to see the proton, you manage to see what is inside. So for instance, if we are in this picture on the left, the wavelength doesn't go inside the proton because it's much larger than the radius of this proton. So you cannot see what is inside. Here they are similar, and we still don't see what is inside. But if at some point you manage to create to throw an electron to a proton, which emits light with a wavelength, so this separation here, that is smaller than the radius of the proton, you see what is inside. And as you see here, there are like a few components that they were called quarks. So with this, they discovered that in the proton, basically, they were 3 quarks, which is 3 smaller particles that made up the proton. So this was very interesting, and this seems very easy, yeah, but it's not easy to do. And actually, I'm going to show you more or less an idea of how this is done, because this is done with accelerators and this detectors. So this is what we all nuclear and particle physics more or less work with right now with this kind of experiments. So to create this current of electrons, to be like a very high energy to emit this photon and see inside the proton, and that's not easy. So I'm going to show you some pictures to make you imagine how SLAC was. So if you look at here, this would be, this is the accelerator. So this straight line here, and it's 2 miles long. So it's kind of long accelerator. And here, basically, we have the electrons, they are accelerated there. So they go to very high energies. And here, in these things here, we have the targets, which are protons. So basically, you accelerate the electrons here and you make them collide with protons that are at rest. And then you detect some particles with some detectors. So this is like a huge experiment. It requires lots of expertise to be created. You require engineers, physicists, computer scientists, and many people to work on this. And also it requires like a lot of budget. I'm going to show you now a picture of the detectors that were on SLAC to show you how big they are. So this would be, here you will have the beam. We call the beam the electrons that are coming, and they will collide here with the target, which will be here, and these things are the detectors. And here you see a human, someone working at the experiment. So you can imagine how big these experiments were. So this is the typical picture of a target experiment. And of course, this was in the 70s. Nowadays, they are even more sophisticated, bigger, and with more layers and detectors. So it's really impressive to do these things. So now, before going to explain you what we do in JLab to understand a little bit more the proton, I think it's important to show you how small these things are, and because it is really impressive that we managed to see things that are that small. So here we have like a scale of things, like for instance, here we have the human beings that are put like at 1 meter. Well, probably we are all a little bit taller, 150, 160, but it's more or less in 1 meter. Here we have the small distance. So this could be centimeters and smaller things. So you think in microscopes, I'm sure most of you have used microscopes in your biology courses. For instance, the normal microscopes, light microscopes that work with lens, can see up to here, which is 10 to the minus 7. 10 to the minus 7 means that if you have 1 centimeter or maybe 1 inch, if you're more comfortable with, you have to divide it in 100,000 parts, all the same, and you will get to here. So it's still a small distance, but the atom is much more smaller than that. Then there are more modern microscopes, which are called electron microscopes, because they don't use light, use electrons, like something like we saw in the previous slide. And they go up to here, which is basically the size of the atom. So the size of the atom is 10 to the minus 10. Basically, more or less all the atoms are the same size. And that's tiny. And that's the maximum we can observe using this kind of microscopes, which are like classical microscopes. But if we go to smaller distances, like the proton that is here is in 10 to the minus 5. So that means that the proton is 100,000 times smaller than an atom, and an atom is already tiny. We cannot do it with microscopes. We cannot do it with this kind of mass microscopes. So that's why we need to build this kind of accelerators, like the one I showed you in the page before. And with this kind of accelerators, you create like giant microscopes that work with beams of electrons. So basically here is the picture. So I'm a nuclear physicist, as Raul is also. And basically we work in these distances here. So we are here, this is the nucleus, which is this more or less, this is what we call femtometers. So basically we work in the femtometer distance, and this would be like a proton or a neutron and the quarks that are inside. And to get inside the proton and the neutron, we need to build accelerators. So now the question is, as they discovered in SLAC, protons and neutrons, also neutrons, are made by 3 quarks. So we have here the quarks. So this would be a proton. It has 2 quarks that we call U type. So both are the same time, the U, and 1 quark that is a D type. So with this, it was like very easy to explain things, because this is from the 60s, 70s, because quarks you are known to have this charge 2/3, and quarks D are known to have minus 1/3. So you sum up two quarks U, and then sum a quark D, which is minus 1/3, you get 1, which is the charge of the proton. So it all works. And then if you do the same for the neutron, instead of being 2 U's and 1 D, is 2 D's and 1 U. And if you do the same, you have minus 1/3 plus minus 1/3 plus 2/3, and it gives you 0. And we all know that the neutron doesn't have charge, so everything looks correct. And also, if you see, we are painting here the quarks in colors, because quarks carry color. Color is something scientists come up with. You can think of color like something like electrical charge. So you know you have positive charge or negative charge, or things without charge. And here the color is a little bit different, because we have 3 colors: red, blue, and green. And what happened is all the particles we see in real life, like protons, neutrons, don't have color, but the inner constituents, the quarks, have color. So to make the proton neutral in color, to have like no color, it has to be formed by quarks of 3 different colors, because when you sum up 1 red, 1 blue, and 1 green, you get something that is colorless in the scientific naming. So that's how we make protons and neutrons. And this all is not something that I'm saying because I like to. It comes with a theory that is called the theory of strong interactions, because the quarks and protons that are inside the quarks that are inside the protons and the neutrons are very strongly bound by a force, which is a fundamental force called the strong interaction. And that means that we cannot just pull out one of these quarks outside the proton. That's basically impossible, because the force is like so strong at that distances that cannot just pull off one of the constituents, which also makes more difficult to study these constituents, because we cannot just pull them out. So the strong force, as I was saying, is one of the force in a fundamental force. I'm sure you have heard about other fundamental force, like the gravitational force or the electromagnetic force. And the strong force is a very strong force, but it's something that it appears at these very tiny distances. So when we talk about protons, and when we talk about the quarks in the protons, the dominant force usually is the strong force. So this force is what it makes that when you have an atom, the protons and neutrons are stick in the nucleus. And now we know that the fact that the nucleus is so tiny, and it's so tiny and in the center of the atom, is due to the fact that the strong force makes the proton and neutrons to be stick all together in a small distance. But it's also the force, as I was saying before, that makes the quarks bind inside the proton. So that makes them to be confined inside the proton. And here we see something else, which are called the gluons. So the gluons carry the strong force. So in the protons, apart from the quarks, the U and D quarks, we have gluons that carry the strong force and make the quarks to be bind inside the proton. So now the question is, so we all know these things. This is something that we know maybe from the 70s. What can we do to understand a little bit more the proton? So what do we do at JLab? So, well, in JLab, of course, there are other things apart from the study of the proton, but what it brings us today here is to talk about the study of the proton. There are many design experiments that try to understand a little bit more of the proton, because even we have learned many things during the last 40 years about the proton, there are still many things that we don't understand. And that's cool, because that means that we have research to do and things to learn. So, I said before that the protons are formed by 3 quarks. Well, so that's not correct. As always, we discover things, and then we discover something else that goes a little bit beyond what we know. So as I was saying before, all these experiments that we made consist of 3 electrons that emit photons to see inside the proton. So originally, when they did these slugs experiments, they see 3 quarks. But what we know nowadays is that if we manage to have these photons with smaller lambdas and smaller wavelengths, we can see even with more detail what happens inside the proton. And we have seen that there are not only 3 quarks, but there are more quarks. The 3 quarks that we said before are the responsible of the charge of the proton, so they are still important. We call them the valence quarks of the proton, but there are more quarks and there are more gluons in the proton. And that's something that we study here at JLab, which is basically, these are all the quarks that exist nowadays, the U, D, S, C, T, and B. Of course, the names are not important. The important thing to know is that apart from these 2 valence quarks, there are more quarks, and depending on the resolution of your photon, you're gonna see something different inside of the proton. So in the early 70s, they only basically managed to have this resolution, and that's why they only see 3 quarks. And JLab now tries not only to see how many of them they are, but also to study their properties and to study how the properties of the proton can arise from the quarks and gluons that constitute them. So this is JLab. So, well, JLab is a little bit different to SLAC of what I showed you before. So this is, even in the picture doesn't seem to be, this is a linear accelerator because it goes in a straight line. And this is like around 8 miles long. So yes, pretty long. And basically here what we do is, well, not me because I'm a theorist, but the people who work at the science and the engineers, they basically accelerate the electrons using electric fields. And here these red things you see are magnets, because charged particles like the electrons can be deviated trajectories with magnets. So magnets are used basically to make them go in this semicircle here. And why do we do this? Because then they can go other linear accelerator. So in this other linear accelerator, they continue to be accelerated. So instead of doing like a very, very long accelerator with this, we can say, okay, they are accelerated here, they turn, they get accelerated again. And we can do this a few times and get them accelerator 5 or 6 times, like 5 or 6 circles. And in that sense, we don't need such a long accelerator to manage to get electrons at very high energy. So that's what we do at JLab. Basically, we accelerate electrons here, and they go 5 or 6 times, and then they go here to the detectors. So there are 4 holes. We call them A, B, C, and there would be here the D that doesn't appear in the picture. And in these A, B, and C holes, and in the D2, there is a target. Usually, you can think of a proton or a small nuclei like helium or tritium or something like that. And you basically make these electrons that go here very, very fast, near to the speed of light, to collide with the proton. And with that, you manage to see inside the proton and study their properties. And things we want to know is not only this picture that we were saying before of how many quarks of each type we have in a proton, but also where are they located. So if you look at here, we also want to know if this would be the center of the proton, where is the location from the center of the proton? And that's more complicated. And actually, this is something that is not JLab, and it's been done for years, but still we don't know much. There are many things that can be improved in this field. To show you a picture of the detector, this is hole B. This is, I think it's class 12. And this could be the detectors. So you can, well, this is when they were being built, basically. And I show you this just to show you how big and sophisticated the detectors are. The detectors are basically layers of different materials. And as we know how different particles are absorbed or behave through these materials, we can basically detect their properties and see which particles we are looking at. So you see these are huge. This is pretty impressive. What we want to know basically at JLab is this picture of the proton. So we want to know all the details of these things in 3D, which is something very complicated that is basically starting to to be precision physics right now, and which will be continue to be done not only at JLab, but at other experiments like the EIC, which is a future experiment that is going to be built also in the US, which has as main goal also study the structure of the proton. And here we see the different quarks that we were talking about inside a proton. So here what we call this U here would be the U quarks, this would be the D quarks. Then we have here the glue, which are the gluons that bind the quarks together. We have here other quarks like the strange. And this is more or less the picture of the quarks that we see nowadays. So this is plotted as a function of the energy. So when we were doing experiments at the SLAB, we were more or less at this kind of energies. And that's why they were only seeing this U and this D, because you were more or less here. And it's basically what you can see. Here, basically, you only see an U's and this. And if you look at this, U, it's like 0.6, and this 0.3, saying that basically 2/3 of the proton at this energy were the U's, and 1/3 were the D's, and which coincides with with their findings, because they were finding 2 U's in a proton and 1 D. But if we go to larger energies, we see that the U and the D decrease, and then, for instance, the glue start to increase. So that means that the composition of the proton depends on the resolution you are looking at. And there are still many here. We don't know. We have like a clear picture more or less of this. But as you see, these bands here is like the error we have to account for when saying that the amount of glues that we have here. So if we want to say how many gluons we have at this point, we don't know if it's the central value will be this black line, but we don't know. This is the uncertainty of this line. So it could be any value between the limit of these colors. So that means that, for instance, the gluons are not very well known, and there is much of improvement to be done there, and that's why there are also many experiments trying to study that. And in JLab, we study particularly also this very high X region here, because this is also not very well known. And something also very interesting that it's being studied is also the mass of the proton. I think I told you before that the charge of the proton is basically the sum of the charge of the valence quarks, so the 2 U's and D that contain, but it happens that for the mass, it's not the same. One good thing, like naively, that basically if the proton is dominated by 2 U's and a D, if you sum the mass of the U's and the D, that will give you the mass of the proton. But it turns out that the mass of the proton, the mass of these 3 quarks is only 1% of the proton mass. And if we even add all the other quarks that appears at different energies, like all the quarks here, and their masses, we don't arrive to more than 90% of the proton mass. So where is the rest of the mass? This is something that we know it has to come from the gluons, and this is from the energy of the gluons that binds the quarks together. But the gluons are massless, so it's not something like very easy, like say, okay, we have the mass of the quarks, the rest is the mass of the gluons, because the gluon is massless. So these are things that still we have an idea where they come from, but still we need to improve both the theory and the experiments to really understand. So there is lots of room for improvement, and I'm sure like in 20 years, someone will come and will give this talk, and they will say that things that I said here have changed, and that's good. That means we are going forward. And just before finishing, I wanted to show you something that I think it's very cool. It's a game. It's a game that was developed by this woman. She's a professor at the University of Michigan. She's very cool. She also works in the structure, or in the structure of the proton and also other particles. And she developed this game that you can download. It's for free. You can download it in the Google Play of your phone. The name is Quantum 3. And it's a game where basically you have to try to find the valence quarks of the particles they tell you here. So here will be a neutron. And if I want to find a neutron, this has to be formed by 2 D's and a U. But also they have to carry all different colors, because all the particles have no color. So this would be a place where I found the two deuterons and the two Ds and the U that makes the neutron, and you find this and you go to a level up and things get more complicated. So you can get strange quarks and things that get more complicated. So I encourage you to download this game because it's pretty fun, it's free, and it allows you to understand a little bit the things that we have talked today, and also other things that I haven't mentioned, like the spin of the particles, and things related to this. So thank you very much, and thank you for your attention. And I will be very happy to have a discussion with you all.
All right. Thank you so much, Carlota. Yeah, I was remembering. So last year, you gave this same talk to another group of students, and you introduced that same game, and that was really popular. People were just
now I decided to do it at the end because people download the game and don't when I do it at the beginning. So now I'm learning from my mistake.
That's very smart. Very smart. Yeah. So thank you so much for the talk. It was really nice. There's a little bit of time delay, so if people have questions, we're going to take a little bit of time before they trickle in. So in the meantime, I have some questions for you, and so I would be interested to hear your thoughts about this. So first, I wanted to hear a little bit about your story. How did you get interested in nuclear physics in the first place?
Well, I think I always I think actually, if you ask me, when I was in high school, I was in love with mathematics. I loved mathematics. I was not in love with physics because I didn't know what physics was, because we used to have like a physics and chemistry course, and most of the course was chemistry. And to me, chemistry, it was like things that I had to learn by heart, and that's it. But one year we had physics, and I love physics, and that got me into physics because it explained you things. And since the beginning, I don't know, I like particle physics for some reason. Maybe it was because I was in Europe, so it was the era of the CERN starting, so we get some information about that, and it seemed cool, and you see pictures. And then I just continued to do that. Well, I don't know. I don't have like a very particular reason to like more nuclear or particle physics than other kind of physics. Probably it was because it was the part of physics I was exposed to at that time.
Yeah, interesting. So we're starting to have some questions. I have more questions for you, but I'll try to intermingle them, pattern with their questions. So first, we have a question from. Actually, we have a clarification from V. Adriana from Mexico, saying, could you please review one more time the segment referred to as mass without mass with quarks and protons?
Yeah, why don't allow me to go back? Okay, let me know. So the idea is that we know the mass of the U and D quarks. And if we add the mass of the U and D quarks, the two U and D quarks that we know they are in the proton, that only gives you 1% of the mass of the proton. So there is 99% we don't know where it comes from. So originally it was like naive to think that only the U and D quarks will give mass to the proton because there are other quarks in the proton. So if you account all the other quarks more or less, you get to 10% of the mass. So there is still more mass coming from something that are not the quarks, which should be the gluons, more or less. But the gluons are massless. So it's not like we know the number of gluons in the proton and we just add their masses and that's it. And we know which is the mass. The gluons do not carry any mass, they are massless, but they carry energy. So the energy, if you have seen this famous Einstein formula, E = mc squared, energy can convert to mass, and the other way around. You can go from mass to energy. So in the end, we know it comes from the glues, from the energy of the glues, but we don't understand that very well. We have some idea where these things come, but it's not like anyone has done any theoretical calculation that tells you 40% of the mass of the proton has to be the glue, or 50 or 20. We don't know. So that's something that is very interesting, because it's funny. Yeah, the protons are in all the atoms, in all the matter we see, and we still don't know where the mass comes from. So that's something cool. and you could probably in the future work on this.
Good. So we have some more questions. So I think this question you probably clarified, but I'll read it anyways. Luis Angel Vergara Ortiz from Hidalgo, Mexico, saying thank you for the very interesting presentation. And then the question is as follows: if investigations have reached this point, what information do we have about gluons? Do they have charge? What are they made out of? Perhaps you can explain a little bit more about the properties of the gluons. Yeah.
So the gluons do not have charge like electric charge, but they also have color charge as the quarks. But instead of having one color charge, they have two color charges. And we know things about the gluons. For instance, gluons can emit other gluons. So that's why we have so many gluons inside of the proton. One gluon basically can be divided into two gluons. Even we have more emissions. So there are many things we know. And this is all in the theory of a strong force. So it's a little bit complicated because I think I never heard about the gluons until I was in my PhD. So it takes some years to read about it, but it's a very fascinating thing.
Yeah, I would say if you don't understand gluons at this point, that's okay. You're in good company.
Yeah, that's okay. Yeah, it's perfectly fine.
They're complicated. Yeah. So we have a nice comment from Jesus Alberto Perez Vargas from Mexicali, Mexico, saying, thank you so much. It took me years trying to understand a little bit of the things that you have in half an hour explained very well. So it's just a nice comment.
Yeah, very nice.
Okay, so we have a long question coming from Indonesia. So let me see if I can read it. So Brian Go from Medan, Indonesia, Brian has been really active in Reyes. So hello, Brian. Saying, good morning from Indonesia. Based on the presentation, there are some questions that I have been wondering. The first question is, how did physicists in the 60s know that there were three types of quarks in protons and neutrons, given actually that there are many quarks inside the protons and neutrons? So I think you touched a little bit on this, but maybe you can clarify that. The second question is, how do electrons and quarks obtain their charge? Good luck in your career in Europe.
Thank you. So I think the first question was
it was how did they see three types of quarks?
Okay. Well, they see three quarks basically because with the accelerators at that time, so that depends on the resolution of your accelerator. So depending on how you manage to accelerate these electrons, this wave that appears here, it's gonna be a little bit different. It's gonna be a smaller or larger resolution power, which is this lambda here. So with the accelerators at that time, they couldn't go further. Basically, they were here and they couldn't go further. With the accelerators we have nowadays, and they're in a slack later, they can go further and see more details. So at that time, it was basically what they show. And as these three quarks that they had could explain very well the charge of the proton and the neutron, they were okay. This response is satisfactory because it explains the things we know about the proton and the neutron. But now we know that, yeah, there are more quarks and more things inside. So the question is, how many quarks are inside the proton? That doesn't have a reply, because it depends on the resolution you are using to look at the proton.
Good. And another question, the second question is, how do electrons and quarks obtain their charge?
Well, that's complicated. Electrons and quarks. Well, that's difficult. So the theory for electrons is not the same as the theory for quarks. So the theory for electrons is electromagnetism. And it's a little bit more complicated to study these things. And I don't know how to reply to this in a way that it's easy to, so Raul, do you know how to reply to this in a way they can easily understand?
How do particles get their charge? I don't know if we know the answer to that.
Well, we don't know the answer to that, but we know some things about that. So yeah, I think we don't know the answer, like how they get the charge, why something gets a positive charge or a negative charge, but we can measure them, and all the particles like electrons, protons that we know have integer numbers of charge, except for the quarks, and that's what we know basically. And we know that adding the charge of the quarks, we can get the correct charge for the proton, but we don't know much about it yet.
Yeah, I would say if somebody figures out, if Brian figures out,
you will get a Nobel Prize probably.
At least we will debate about it. If Brian figures out, how the electron gets a charge, then maybe we'll have an argument about whether he should get the Nobel Prize or not. Okay, so we have a few more questions. First, just a really nice comment from Thalia from Stafford, Virginia. Great talk today. I learned so much about protons and the inside pictures of the Jefferson Lab. It was very cool.
Thank you.
So we have, it is a complicated question. So we have a couple complicated questions. Let me see if I can read them and maybe you can decipher them. The first one is from Jorge Benel from Lima, Peru, saying, thanks, Carlota, for the great presentation. I have one question. In the plot in slide 15, you say the up and down quarks are about 2/3 and 1/3 at certain energy levels. As we can see, so perhaps you want to go to, do you have that slide? Good, okay. As we can see in the peaks of the graph, so that's, sorry, so 2/3 and 1/3 as we see in the peak of the class, of the graph. But in the plot, it says that the energy, Q squared, is fixed, and the x-axis, the Bjorken, I think, is the one that changes. Does that plot show how it varies at different energies?
So, well, that's a difficult question. Probably, I didn't talk about Bjorken X or things like that because it's something very deep. But this is varying the center of mass energy of the experiment, so what we usually call square S. So basically, X is proportional to Q squared divided by S. So basically, if Q squared is fixed, when you go to lower X, you are going to higher energies. But this is the energy, the center of mass energy of the scale of the experiment. So yes, going to lower X is going to much energy. It's true that Q squared is fixed. Q squared is the resolution. So Q squared is basically what tells you the resolution you're looking at is related to this lambda that I was showing in these plots before. So depending on the resolution, you may see one thing or another. That's also true. But the variation with Q squared, that's something we understand. That's probably one of the few things that we really understand. What we don't understand, I mean, this is something that we extract from data. This is something that we can learn from the data, but this is not something we really understand why is like this or not a little bit more larger here or smaller. This is something that still needs to be investigated. But it's true that it can be a little bit misleading what energy I'm talking about here. It's the center of mass energy.
Yeah, that was a great question from Jorge.
Yeah.
Sounds like perhaps Jorge has some.
He knows more, yeah.
Yeah, it sounds like he has some physics background. Jorge, if you're interested in nuclear physics, maybe you should send us a message. Okay, so we have another question. This one's a little tricky, since maybe for not experimentalists. So I'll let you handle it. It's from again from Luis Angel from Hidalgo, Mexico, saying, for the experiments, do you use pure protons and pure electrons, or the materials themselves, like elements? So are targets?
That depends on the experiment. I think you have a talk about CERN a few weeks ago. So for instance, in CERN, they accelerate protons, and that's pure protons. They accelerate protons, and basically it's different from this one because here in Jefferson Lab, we accelerate electrons. So in CERN, it's protons, here it's electrons, and these are pure electrons. And here we have a target, and we just collide the electrons with the target, which is not moving. It's a target. It's just make them collide. The target can be protons, but in JLab most of the time is small nuclei. So it's like helium or tritium or something like that. In CERN, where they do a different kind of physics, so they want to study different things that are also very interesting, they collide protons, but both protons are moving. So yes, you can collide. And also there is like a special run where they collide, instead of protons, a nucleus of lead. But in the accelerators, you have always to collide charged particles, because that's the only ones you can accelerate. In this kind of accelerators, there are photon accelerators and other things. But for what the physics we do here, it's always electrons, and the targets can be nuclei or protons.
Great. Okay, so we have a few more questions. They keep trickling in. So we have one from, let me read the longer one. So we have one from New York, Jonathan Cheng. Excellent presentation. It was interesting to see how Jefferson Lab is doing to understand fundamental particles. In the chart about proton structure, we see that the increased energy is associated with the increase in gluons and strange quarks. Why are strange quarks being created disproportionately with up and down quarks? In addition, does the varying number of virtual particles mean that different protons can carry different measure mass?
I don't know if I understood the
second one.
The second one, but I'm gonna start by the first one.
I think the first one I understand. The second one I also struggle to understand.
So well, we know this. So if you see here, he's right. The gluon is growing up. It seems that it grows forever, like from this curve. It cannot be true, because these are like probabilities. So the maximum, the sum has to be 1, basically. If you sum the probabilities, this would be like the probability of finding a glue in a proton. So if you go to larger energies, you find more glues, and this is true. This comes from equations. So basically it's not easy to explain, but we have some equations that explain these things. But it's true that it seems that it grows up, but it has to saturate at some point. So that's also something very interesting in nuclear physics, because we all know that at some point this has to stop growing and has to saturate, cannot go beyond 1, basically, because that makes no sense. But we haven't never seen that regime in experiments. We have never measured that. So that's something very cool that maybe it will be done at the EIC, maybe not, we don't know. And that's something we all want to see. And it's not an open question, because we all know it has to saturate, but when it has to saturate, that's an open question. And regarding the strange, even here, it seems like very well determined. It doesn't have like such a big background as the glue. It's not true. There are many things that we don't know it still about the strange. It's difficult, and actually there are experiments that report results that seem contradictory. So there is lots of research to be done there, and it also comes from equations that basically you can generate. So basically what happens is that you generate more gluons, and gluons can radiate the strange, and it's all correlated. Basically, the fact that the glue grows, it also correlated to the strange, but it's something still under research. And there is also something that I didn't say here, but this region here, even if it seems the same as these other regions, here, basically, this is all extracted from data, but in this region, we don't have many data. So many of the things that we see in this part here are just extrapolation of what we see here. It's like you plot something like that, and you just continue plotting. So the very high energy region is still something we really need to learn a lot from.
Great. And I should have mentioned that in our Python for Physics course, people were really, the course that me and Ted are teaching, some people asked us about if we could give an overview of PDFs, of parton distribution functions.
Wow.
So there was interest. I gave a little mini one, but you're certainly an expert, which I'm not. So they get a little bit of taste of this here. Okay,
it's difficult. There are many things we don't know yet, so we need more nuclear physicists working on this.
Yeah, I mean, my impression is that this is a field that is still growing. I mean, as you said, there's many questions still to be answered, and there's now, I mean, the methodology for extracting these from experiments as well as from pure theory are growing. So there's a lot of opportunity. So, and as you mentioned, we just got the Department of Energy to approve the electron ion collider here in the U.S., and so this is a field that is still going to get funded. And so there's a lot of opportunities for physicists, not just in the U.S., because I mean, I don't know if you noticed, but Carlota and I are not from the U.S. Originally, but we've come here now to work. So we need physicists from not just the U.S. but all over the world.
Yeah.
Okay.
Yeah,
So
if you're interested in nuclear physics, it's a good time to start, because with the electron ion collider coming, which is something that is coming, but it will come in 10 years. So in 10 years, we will have a new experiment running, having new data to analyze. So even if you like to be more experimentalist and just go to the experiment, analyze data, you're going to have lots of fun and lots of work to do. And if you like to understand these questions from the theoretical point of view, there will be more data. So we could work even in more things.
No. Okay, so I think we have time for one last question. And so mentioning that we need scientists from all over the world, this question is coming from India. The person is Shrivishnu, who has participated in many of our REYES activities. And there are two questions, actually. And I think these touch at the core of quarks. So the first one is, can quarks be isolated by using accelerators in detectors? The second question is, the mass of the top quark is equivalent to hafnium nucleus, which I had to look it up. So it's apparently a top quark is the same mass as a really heavy nucleus. How is it possible for a quark to attain such huge mass?
So, well, it's true that the top quark is very, very massive. Actually, if you look at these plots here, it never appears in these PDF plots. So we never managed to do the top. We never radiate top because it's very massive. But yeah, the top quark was discovered, I think, in the 90s or something like that, and it's very massive. It's complicated. What was the other question? The quarks?
Can quarks ever be isolated in an accelerator detector?
That's I would say first it's impossible, but then I will clarify. Okay, so yeah, the problem is that the strong form has this name because it's very strong. So that means that you cannot just pull out a quark from inside a proton. So basically you cannot separate a quark from the proton. But there is something that it can be, and it's done at both at CERN, the accelerator that is in Switzerland, and also at Brookhaven National Lab, which is a lab that is here in the US, is in Long Island near New York. And they have a program of nuclear physics, which is different from the program that we have at JLab. So it's complementary things of nuclear physics. When instead of accelerating electrons like we do here, or protons like they do most of the time at CERN, they accelerate heavy ions, which means very heavy nuclei, like nuclei of lead. And when you do this, you manage to get a collision of heavy ions. What happens is it's a collision that is formed at very, very high temperature and energy, because these are heavy ions. And in this case, only in these conditions, you manage to have like a soup of quarks and gluons. So it's not they are isolated. You cannot get just one quark, but you can manage to break the proton and have quarks and gluons in a kind of fluid-like thing that is analyzed in these experiments. That's also pretty cool.
All right, so I think we've run out of time. I think we could have kept asking you many more questions. Let me press one more time the gratitude that we have for you taking time out of your schedule to give this talk. We very much appreciate it. And I think from me and everybody else in REYES, we wish you a lot of luck in Europe and a lot of success in your next two career paths. So thank you so much, Carlota.
Thank you all for listening and asking so many interesting questions.
All right, thank you so much. And That's all we have for you today in Regis. Join us back again tomorrow. As I mentioned, Python for Physics will not take place, but you can still, if you have any questions, you can still forward those questions to us. But we will have the activity that follows after Python for Physics. Everybody have a good day. Stay safe.